What's up? What's up? What's up? What's up? We gotta go on here. Alright. People tripping out a little bit. Alright, we back. We good. Alright, so this video, as you can see, is an introduction to gravity and orbits. I saw this video, I wanted to do a review on it. Yo, RIP to the globe. But it's cool. So this is what I'm doing here. I'm looking at this video and I'm like, oh man. I'm like, look at how that. Let's just go. Let's go.
In 1666, during a horrible pandemic that forced the closure of businesses and schools throughout England, a bright young math student from Trinity College in Cambridge sat beneath an apple tree on his family farm while contemplating the esoteric subject of celestial mechanics, the physics of the heavens. At the time, the heavens and the earth were thought to obey two drastically different laws of motion prescribed by Aristotle. Motion on earth was evanescent and governed by transient forces within our intellectual reach, while the motion of the heavens was eternal and governed by arcane forces beyond our grasp. The story goes that while the student was pondering the orbit of the moon around Earth, an apple fell from the tree and struck him on the head, delivering a profound epiphany. In that moment, the young Isaac Newton realized that the same gravitational force which pulled down the apple is also pulling down on the moon. This story of revelation.
See, okay, so we're going to present this thing from this particular point of view in which they have introduced it. Gravity. Let's look it up. Let's check it out. Let's look it up. I ain't really come to play with y'all, man. I came to get y'all to see the same truth I'm looking at here. All right. In physics, gravity, from Latin, gravitas, weight, all right, is a fundamental interaction which causes mutual attraction between all things with mass or energy. A mutual attraction. That's hardly gravity that he's speaking of. Gravity is by far the weakest of the four fundamental interactions, approximately 10 times weaker than the strongest than the strong interaction, 10 times weaker than approximately 10 times weaker than the strong interaction, 10 times weaker than. Let's get this thing. Let's get this, man. Let's look at this thing. Like I said, I ain't gonna play. Let's not play. Let's read a little more of this thing. Approximately weaker than the strong interaction, 10 to the 36 power times weaker than the electromagnetic force. So it's weaker than the electromagnetic force, quite weaker than electromagnetism. So we're not speaking of magnetism. Let's make that clear. This thing is way weaker than electromagnetism. However, gravity is the most significant interaction between objects at the microscopic scale. Okay, so it says, however, gravity is the most significant interaction between objects at a macroscopic scale. That's macro scale. That's the big scale. Micro, small. Just for y'all who don't know, we ain't gonna laugh. We're gonna keep it moving. All right, because we gotta make sure it's all known. Did I skip a whole level here? Yeah. As a result, it has no significant influence at the level of subatomic particles. So look at this thing. I don't know how many people actually know the definition of gravity. Look at this. It is 10 to the 36 times weaker than the electromagnetic force, right? 10 to the 29 times weaker than the weak interaction. Okay. So electromagnetism is stronger. Here we go. The aurora borealis looks like here. We ain't gonna get into that. That's all flat Earth anyway. We're going back to the North Pole. But as a result, it has no significant influence at the level of subatomic particles. So subatomic particles don't move off of this imaginary force. Gravity only works, it says here. However, gravity is the most significant interaction between objects at the macro scale. So how come it doesn't work on small levels, but it works on big levels? It was strong enough to make an apple fall on this man's head, right? But it was too weak. It's too weak for atoms and all of that to have to abide by this law. Subatomic particles don't have to abide by these things, but our sun does. The stars in the sky do, but the subatomic particles don't. See, people get it twisted. They're saying, hey man, it works on all the scales. No, it doesn't. According to the definition, it does not. It has no significant influence at the level of subatomic particles. And that's real, right? Right? Here it even says it, okay? It works on a microscopic level scale, and it determines the motion of planets, stars, galaxies, and even light. Light exists on micro level as well. Light exists on subatomic levels. Okay, the electron is a light particle. All right, it's light. The electron is lit up. If you study electricity, you know that's how electricity works. Okay, they use current to push the electron. That's the electron you see jumping the electricity, and it's moving towards a positive terminal. You guys have got to see what's going on here. So gravity don't govern light. It don't. Otherwise, it would govern a subatomic particle, like an electron. An electron would go by the same. See, a lot of people don't know that electrons have weight. They're not weightless. They have weight. So everything that has weight is what we're taught. The overall thing of this thing. Hey, everything has gravity. On Earth, gravity gives weight to physical objects. Okay, what is a physical object? I'm sorry, Sam. I want to give y'all, and we got to get back to this video. I'm reviewing this video, but I'm breaking this apart, man. Where I'm seeing what needs to be broken. In common usage, the classic mechanics, a physical object or physical body, or simply an object or body, is a collection of matter within a defined contiguous boundary in three-dimensional space. Okay, the boundary must be defined and identified by properties of the material. So you have to have material to create an object that has to be made of thing. It has to be a sum of things. Something is actually a sum of things. All right, and that's what they're telling you here. They're telling you that it has to be materials. Okay, the boundary may change over time. It may change over time. The boundary is usually visible or a tangible surface of the object. The matter in the object is constrained to a greater or lesser degree. This is an atom we're speaking of. So atoms should have gravity, right? They should go by gravity, but the thing says subatomic particles don't follow this law, right? They don't, because everything follows density anyway. Density and buoyancy, and that's what they're describing. If you want to describe the apple falling on the man's head, we will use the word density. That's to make things fall. Look, 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 man. Let's get back over there. Okay, I'm gonna take another maybe minute or two describing this thing. Let's look up density while we in it. Right. compa- competence, compactness of a substance. All right. Synonym: solidity, solidness, denseness, thickness, substance. Okay, density, atomic mass, density, or specific mass is the substance mass per unit of volume. The symbol most often used for density is P. Okay, yeah, they going into it. They ain't really going into it. A measure of the amount of information on the storage. Okay, yeah. Oh, look at this specific gravity. Check this out. Okay, specific gravity is the ratio of the density of a substance to the density of a reference substance. This is called specific gravity. This is used in electronics. This is what engineers use. See, engineers use this stuff. This is a specific gravity table chart in the equations. But they when they go and use it, they tell them, look, specific gravity is the ratio of the density of a substance to the density of a reference substance. And that goes back to like weight, volume, and all of that. It gets way deeper when you get into, okay, the reference substance is nearly always water at its density for liquids, and for gases, air at room temperature. Okay, so the reference substance is like water. Okay, room temperature water is what it is. What I've been taught is water. All right, so they use water as the base, right? Water at room temperature, because the temperature does make a difference. Okay, so this is gravity. So once again, a hot object weigh more because it have more it'll have more electrons in it, right? While it'll have more electrons moving in the covalence belt. My bad, covalence. What is that? Valence belt, right? It's more active, more energized. While cool has less. It got less energy to it, right? So this is gravity though, and weight and shit like that they're talking about. You got to understand it's deeper than like I was just showing you. Density has a far more deep definition when it comes to breaking things down. And even when I showed you the scientific gravity that's used in engineering, they could use specific gravity, and it's density all over this definition. Look, it's density. The first sentence is density, and it's in it twice. And it's talking about the density of two different substances. It don't say nothing about gravity. It don't describe. It don't describe gravity with gravity. You can't describe it like that. Some words they use the same word to describe it after they kind of stretch the word out and kind of describe the word a little bit. You can't describe gravity like that. You have to have density to describe gravity. And then density only describes gravity. Gravity don't describe buoyancy. Okay, let's get back. My bad for that break.
Is probably just a story that Newton made up, but the iconoclastic scientist could not have chosen a better fruit to symbolize the incredible knowledge he discovered about gravitation.
I'm so sorry. He just talked about the tree. Let's hit up this tree real quick. This tree thing, because if you go back to Egypt, a lot of these guys sat under trees. Um, Tahuti, it's a story where Tahuti sat under a tree. Buddha sat under a tree. It's a lot of guys. The trees are really known, and the like in like India, like you got the Buddha tree. You got trees that are the fig trees are really known, are really big in different areas, right? They have to go by different names and such. You got trees in Africa. like that too, right? But it's always a thing. It's like the tree thing, right? If you think of the caduceus is a tree, and it's here this guy is sitting under a tree. This he's definitely a cultist, right? Because all of these guys are cultists who were the inventors and got their name put in these books. If your name was put in a book, you was an occultist. That's just how it is. I mean, they looked out for their own. They don't look out for those who ain't with them. They gonna take your stuff, and that's just how it is. If you ain't with them, you ain't down, and they just gonna take your stuff. That's just the name of the game. Um, but this tree thing, it always this dude goes back and gets hit with an apple. Okay, what happened at the garden when Adam and Eve was at the tree? Oh, it was biting the apple. So this is like us in a way. This man sitting at the tree and chilling while all of this turmoil is going through. He's not in a garden of Eden. He's in a garden of like chaos. And he's falling and he's hit this tree and he's receiving this knowledge that's falling. I know y'all gonna say I'm reaching, man, but y'all don't get y'all gotta be able to connect things a little bit, man. It's the reach party. It's just what we do here. You gotta be able to think a little bit. Ain't nothing I'm saying wrong, though. You can't say any of the symbols I'm saying don't line up. All of them line up. It ain't debatable. But yeah, let's keep it moving.
Which united the physical laws of heaven and earth and enabled humans to visit other worlds.
Make sure that you've got your feet underneath you.
Hello everyone, I'm Jesse Mason, and in this video, we'll learn about gravity and orbits. That seminal year on the Newton family farm yielded 4 major discoveries that rocked the world of science. The first was his laws of motion.
Okay, this is one of the parts I was really wanting to go over when it got to it. Okay, so once again, we was talking about the tree. Right, here we go with the 666. This all happened in 1666. And you might say, oh, that's ironic. But I don't see 166. I see 666. And I see this guy sitting in this garden of all type of carnage going on around him. And in it, he had this idea where Adam and Eve were in a garden, and they had an idea. I see this guy is basically in hell, and he's sitting at the tree, and he has this idea. Okay, that's how I see it. Okay, but that's beside the point. I want to look at these things. He's going to bring up these points here. And we're going to go through those as he goes over them. We're going to go together. So let's go.
Which upended 2 millennia of thinking on the subject. Aristotle had people convinced that forces cause motion, but Newton demonstrated unequivocally that forces do not cause motion, but rather change motion. Much of introductory physics consists of the innumerable applications of these 3 thrilling laws. Newton's second discovery explained the
Okay, so the first discovery, 3 laws of motion, right? Forces do not change. Objects create the force, or do force change the objects? Okay, so when we're speaking on electricity, you got your source, right? And your source provides you a current, and the current pushes the electrons. It pushes the objects. If you pushing a computer like I'm pushing now, right? And I'm pushing the electrons through it. If you pushing that, then it actually powers. It pushes it pushes objects, right? Force pushes objects, right? So that's real, right? Wherever the source is, it's coming from. That source pushes objects. So we're gonna go into that. That's good.
composition of white light, which had always been regarded as the purest form of light. Through clever experimentation involving prisms, Newton showed that colored light is actually the pure form of light. That year, he also discovered.
Okay, so now here we go with the BS. If you study a prism, You know the most purest form of light is white light. Okay, you know that colors are the breaking down of the light. The colors are actually the light being broken apart. It's like this. If you think of a white light, you think about the source of that white light. Okay? Think about the source of it. Now, the light comes down white. It's white. It ain't colored. How can it be pure if you have to take it out of something? The most purest form, and then so what you mean? Red, blue, white, yellow, red, blue, yellow, green, all of this is more pure. No, no. The most pure form of light is white light. And then once we get into it, we start to look at white and blackness and see them as reflections of each other on different dynamics. But this here, I think, is the first confusion that he's thrown out in his theories so far that we just accepted as facts. That white light is actually the most purest form. I mean, that the colored light is actually more pure than the white light. Nowhere does that make sense. That's laughable. I mean, all the religions. We talk but it's laughable. It is laughable. Nowhere. And I mean, all the other religions teach about the white light. All the other cultures, everybody knows that the white light is the most purest, and that the crystal breaks down the white light. So you're saying the red is more pure than the white light? No, they all make up each other. This is like division and breaking people apart. This type of knowledge that gets you to where now you're saying that the colors so you're saying that the colors of each individual race is more pure than the colors of all of the races put together. You're saying the black race, the Asian race, the white race are more powerful separated than they are coming together and working together. See, it's a way of thinking. It's like the science that they give you. They draw these boundaries and they give you subliminals. So when you accept this thing, it's easier to accept other things, you know. Let's keep it moving. That's what the third joint is.
Discovered a useful form of math, which he called fluxions, but we now call calculus, which helped him explain the changes in motion that his three laws described. His fourth discovery of 1666
All right, let's go back to that one. So I was going to go over all of them. My bad, I kind of missed out.
light. That year, he also discovered a useful form of math, which he called fluxions, but we now call calculus, which helped him explain the changes in motion that his three laws described. His fourth discovery of 1666, delivered by messenger Apple, was that the phenomenon of gravitation is universal. Newton explained this final discovery using a wonderful thought experiment featuring a powerful cannon on a mountaintop. In honor of
We got to break this down.
Newton, we'll use apples instead of cannonballs. Suppose an apple is launched from a low-power cannon atop the mountain. The apple would arc to the ground a short distance from the base of the mountain. Now, a medium-power cannon would launch the apple even further along the curvature of the earth. A high-power cannon could get the apple halfway around the planet. You see where this is going? If we had a cannon powerful enough, and if our atmosphere wasn't such a drag, we could give that apple an initial velocity so great that the arc of its trajectory would match the curvature of the Earth. So as the supersonic apple falls toward the ground curves away from the apple at exactly the same rate.
Okay, has anybody ever witnessed this shit going down? This is laughable. The way he just broke this down is crazy. Do you know how much, like, you can't prove this, man. You're just telling, it's a concept. It's a theory. Look, you can't put a globe in the middle of the thing and then say, yeah, man, we could just shoot things around it and it'll just. You can't just do that. So often up and we just take these drawings and stuff, these concepts, and we don't really think about this thing. Have you ever known of anybody? They used to do that in the cartoons, throw some stuff up in the air, in the atmosphere, and it just pop back around and pop you on the other side. No. When has anybody ever done a experiment? If we had a cannon strong enough, does anybody have a gun strong enough? This is laughable. Truth is, right? They're talking about shooting it at a particular angle to where it'll go all the way around. Now he's talking about satellites, shooting satellites and all of this stuff, but it goes into an invisible thing. Now we can't prove this stuff. We can't prove this. This is laughable. Did you see what he just put on the screen? I don't know how, if this is really Isaac's theory or it is dude theory. But let's keep it moving.
And eventually,
By the way, on a flat earth, if you got a flat plane, right, and you hear, and you shoot a cannon, pow, with a trajectory, it's gonna go a little bit. And you hit it a little more trajectory, it's gonna go further. It's gonna go further. It works like that on the flat earth, bro. That's how it works with a basketball. Nothing to do with the earth curvature. It's how you curve the object, and it's based on a flat surface. Ain't nobody equivalating for no freaking man. It's this is how submarines work, bro. This is crazy. I'm sorry. Let's keep moving. I don't want to hang up on this. This is just too crazy for me.
the apple would return to the mountain from whence it came. And if we could somehow move our mountain out of the way, the apple would become a satellite, orbiting Earth at the same altitude as the elevation from which it was launched. The moon, Newton realized with this thought experiment, is simply Earth's natural satellite, falling toward the Earth like the apple, because it must be attracted toward the Earth like the apple. Gravitational attraction does not belong to Earth, it belongs to the universe.
He just macking about how the moon is falling to the earth and all of this and that. Let me ask you this. They say that the moon is falling to the earth. If the moon is falling to the earth and the sun is getting closer to us, then how come we consistently, year for year, for thousands of years, it's never been documented that we ain't. It's always been documented of us seeing an eclipse. If these objects are actually moving, how come we always see a perfect alignment? If the earth is getting closer to the sun is getting bigger. Okay? If the moon is getting closer, the moon's getting bigger too, right? So, but they're never at an exact same away from each other because the sun is revolving around the earth in an oval like that right there, right? While the moon is also doing the same thing. While they're all getting closer. So they move out of alignment. Then every time they line up for thousands of years, every time they line up perfectly, man, that's laughable. None of it makes sense. Have you seen the model of the universe that they give us, man? Of the solar system where we're all just coiling through outer space? And we're supposed to just believe that this gravity, and then once again, it don't work with me in this lighter, right? The lighter in here. It don't work like that. It only work, right? Because this is, what is this? This is lighter than this, right? So it should be moving around it or attracted to it or something. what's going on with this? What's going on here?
That's the heart of Newton's universal law of gravitation. Simply put, massive bodies, no matter their separation, are attracted to other massive bodies.
I'm sorry, y'all, but okay, I gotta go. Each point, it's another point here. Massive bodies, no matter their separation, are attracted to other massive bodies. That's laughable. That's laughable. Mass is perception. Okay? To an ant, you a giant. To a microorganism, you're like God. You're so big. Like, what is mass really? At what level are you speaking of? Even of the scale of 1 pound, 2 pound, 3 pound, that scale is based on the level of the dimension that we're in, where we see things. Trees are giants to us. So to a tree, a pound might be different. If they're judging us a pound off of their scale, if they created their own scale, we would be negative to them, just like microorganisms are negative to us. Just like an ant don't even weigh a pound. Because of our scale, it's perception. So if gravity works here, it works there. I want you to understand this thing here. Because these are perceivable things. These are you can't say it works like that on all levels, because it only works like that on our level. Not honestly, it don't even work like that on our level. The definition said that it only works on these big bodies, on these celestial type bodies. What did the definition say? Density, gravity. What was it? It says macro. However, it says it has no influence at the level of subatomic particles. However, gravity is the most significant interaction between objects at the macroscopic level. Macro, micro is perception. It's like where do you put the base point? There's a median point in which you judge things, right? And that's based on your perception. We're all humans. They say the average human is this tall to this tall. The average baby is this weight to this weight. So they can say the babies have a scale. Humans are they're on a scale. Women's shoes are different from men's shoes because of the scales. So you can't judge this thing and say, hey, well, it works on a microscopic level, but it doesn't work on a subatomic level. I mean, what are y'all teaching us here? And then this guy says that no matter the separation of the bodies, that it works on a massive level. To ants, we would be massive. Why aren't we having some type of attraction when we're just revolving around each other in the air, in the atmosphere, or whatever? Like we're having to pull. We don't feel that. Okay, let's just keep moving here.
Now let that sink in for a second. So, this chair is attracted to this desk, the mountain is attracted to the apple, and I'm attracted to the moon, to Saturn, to a black hole we imaged not long ago in a galaxy far, far away? Yep, you can't feel it, but everything with mass is pulling on you.
That's crazy. Man, this is gonna be a long video. It's gonna be a long night. Yo, but I gotta break it. Look, that's what I was just saying. You can't feel it. This is what I was. It don't work on this level. It don't work. A pin. Oh, I'm attracted to. Look, I'm attracted to the moon. What? No, but you just don't feel it, right? I just don't feel it. Hell, I'm attracted to Saturn, to the black hole near away, even though it ain't pulling me away. The pen, I'm attracted to the table. Look what he said about the table joint. My bad, my daughter came in.
and I'm attracted to the moon? The mountain is attracted to the apple, and I'm attracted to the moon?
The apple is attracted to the mountain because the mountain will be bigger. No, it don't work that way. Everything falls straight down. Straight down. No, nothing fall to the side. Gravity and then with the spin, it don't fall because it's spinning or nothing. It only fall because of air, and that's like the pressure in the atmosphere. That's something like the wind is something like the current and electricity pushing the electrons. Right. That's what pushes things. That's the push. We ain't. I mean, that's the push we experience. We don't experience no pull. The moon ain't pulling me upward. Do the moon be pulling you towards it? Do you know where the moon at? Because it pulls you towards it. Do you know where these planets at? Because they pull you towards them. Do you know where the table's at? Because you're pulled towards it even though you can't feel it. A lot of us meditate. Are we pulled towards tables and chairs, man? Come on, man.
To Saturn? To a black hole we imaged not long ago in a galaxy far, far away? Yep, you can't feel it, but everything with mass is pulling on you. The idea that gravitational attraction applies to all bodies and extends all the way across the cosmos was a hard pill to swallow. But this elegant law explained the motion.
It don't. We just read it don't. It don't apply to everything. It's a misconception. We need to know what we're really talking about. What is he talking about? It don't apply to everything. It only apply to your solar system that you created. The solar system that we can't prove because we can't do it there. Y'all did. Armstrong and all of them went up there. Congratulations. Yay, good for Armstrong and all of them. You know what I'm saying? It's your boy Tesla Elon. Elon went up there. Thanks, Elon. Appreciate it. We ain't gonna never go though. We're never going. It don't work. Let's go.
Of the moon, the motions of the planets, and the motions of moons around other planets. And it accurately predicted for the very first time in human history the arrival of a comet. The simplest case we can depict graphically is that of two spherical bodies with force vectors indicating mutual gravitation. These two forces are equal in magnitude but opposite in direction. Equal but opposite. Does that ring a bell? Yes, these two forces do constitute a Newton's third law pair, which means not only does the Earth tug on the moon, but the moon tugs back on the Earth. Of course, we have an equation that quantifies Newton's qualitatively incredible law. Fg equals g times m1 times m2 over r squared. Here, Fg is the gravitational force in newtons. M1 and M2 are the body's masses. R is the distance between the body's centers of mass. We'll learn more about center of mass later, but for now it's sufficient to say that the center of mass of a spherical body like a planet or a star is at their geometric center. And lastly, big G is the gravitational constant, which is equal to 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared. We'll call it big G to differentiate from little g, the acceleration due to gravity. Big G is one of a couple dozen constants that we will encounter on our learning journey together. It is far more fundamental than little g, which, when we get to force fields, we'll learn actually comes from big G. Big G.
So how he put this thing together, the big G is one of a couple dozen universal constants like speed of light. Well, I thought that God was light, right? So a lot of y'all, you might not be religious listening to this, right? You ain't gotta be. You need to have an open mind. I'm not religious. I don't have no. You trying to see what I'm rocking? I ain't rocking no cross. This ain't no cross. Don't get it confused with a cross. Definitely not a cross. Big G, little G. It sound like big God, little God. What the little G do?
Is one of a couple dozen constants that characterize our entire universe, which, as far as we can tell, don't change with respect to space or time. Universe is one of a couple dozen constants that characterize our entire universe, which, as far as we can tell, don't change with respect to space or time. If big G were just a fraction of a percent larger, making the gravitational attraction a little bit stronger, or a little bit smaller, making the gravitational attraction a little bit weaker, none of this, the chair, the desk, Saturn, you or I, none of it would be here. And the same goes for the other physical constants.
This is what I'm saying. This big G, little G thing, and then it goes back to who else got the G? The Freemasons. They got the G on their thing, right? Everybody with this G. Here we go back to gravity. When if we was dealing with density and buoyancy, we're not even dealing with this G, this Masonic G. They just keep throwing around. Now here he is to describe it. He's talking about another big G and a little G. This is what I'm saying. It's going back into religion. It's like this ain't what this about. We about to keep on with this. It's gravity thing. It's flat Earth. Flat power. Flat power.
Is our universe a finely tuned instrument for playing the song of existence and of life and consciousness? Sounds like it. Are there other universes out there playing out of tune, so to speak? Some scientists think so. Perhaps there is an infinite orchestra of universes out there playing an unfathomably complex symphony of existences, and we just happen to be playing first violin at the concert. What a thought. Now, before we tackle a problem using Newton's universal law of gravitation, I'd like to point out that new log is our first inverse square law, which is to say, this is the first of several laws we'll encounter in physics, which the strength of the phenomenon, or flux as physicists refer to it, decreases with the square of its distance. So if we were to double the distance between the two bodies here, the gravitational force between them would be a quarter of its original strength. Tripling the distance would decrease it to a ninth of its original strength. Exponentials tend to explode in size, which is why massive bodies like our moon have little effect down here on Earth. Sometimes, though, those little effects can add up, which is precisely the case for our moon and the oceans. The tides, Newton correctly observed after discovering his gravitational law, are a direct consequence of the tiny pull exerted by the moon on zillions of tiny water drops in the ocean. Okay, let's tackle a problem using our new tool. Let's find the speed an apple would have to be moving to stay in orbit around Earth. To make this silly problem a little bit more realistic, we'll elevate the apple to, I don't know, let's say 420 kilometers, so very high that atmospheric drag won't be an issue for our apple. First things first, let's draw a picture. We always DAP, draw a picture, when solving a physics problem. So here's the Earth, and here's our apple moving in circular orbit around the planet, traveling at some terrifying speed. Definitely wouldn't want to get hit in the head by that apple. Since we're looking for the speed, we'll give it a $sign, indicating once we've found that value, we are in the money. Speaking of values, let's write the only value this problem lists, which is the altitude of the apple. We'll assign the variable h for elevation, and if you're like me, you want to convert that value right away to meters. Equations say yes to the MKS. Units, that is. Okay, we've got a bit of room left, which we'll save just in case we need to look up any other constants for our problem. Yes, we will need the gravitational constant. Why don't we write that right now? Big G equals 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared. All right, on to the equation step. This is a new log problem, so we'll start with the general form of the equation. And then we'll modify it to reflect the two bodies in question, the Earth and our astronautical apple.
Sorry, all my kids.
Now, before we start digging up Earth's mass, etc., let's look at what...
I'm just going to keep moving and jump in on with it, though. I ain't even going to go back. Just try to pick up on what's going on. That's what I've been trying to do. I ain't said nothing. Let's keep moving.
We know about the gravitational force here. We don't have a value for this force, but we do know that it is responsible for the apple's uniform circular motion around the planet. Recall that uniform circular motion is characterized by constant speed with a constant perpendicular acceleration, or centripetal acceleration, which requires a centripetal force. The centripetal force that moves a body in uniform circular motion can be calculated by multiplying the mass of the moving body by its speed squared and dividing by the radius of its curve. The gravitational force is the centripetal force on the apple. So we can write mv squared over r equals big G me ma over r squared. This m here is the mass of the apple, so we'll add that subscript. And now we solve for v. We'll multiply the whole equation by r over ma, dividing out one of these r's and both masses. And this yields an amazing result. The mass of the apple won't affect its orbit. It could be the size of a football field, and so long as it's moving at this speed, it'll maintain an orbital altitude of 420 kilometers. By the way, to get rid of that square, we take a square root of both sides. Okay, now what about this r here? Remember that r is not the distance between each body, but rather the distance between the centers of mass for each body. So we need to add the radius of each body to the distance between them to get the distance between their centers of mass. Even if it were as big as a football field, the radius of the apple is insignificant compared to its altitude and Earth's whopping radius, so we'll ignore it in our calculations. And then we can finally look up the mass and radius of the Earth. We'll put both of those next to our picture in case we make a mistake and need to retrace our steps. And we'll convert.
My question, like, okay, I'm seeing the math. Okay, this is the part 2 of the math, right? This, right? So, with all of this, the only proof that we have of this thing working is, okay, so I see a lot of, like we just read the definition of density. We ain't gonna go back and do that, but we did it. And I see, it reminds me, this formula is reminding me of the definition of density. Like, once again, like describing these things using density, all you gotta do is just change the word, right? And they can just make, but then gravity don't describe it, just describes the fall of things. It don't describe its rise. You know, according to gravity, what goes up must come down. That's gravity. But density, they say what goes down must come up. Because now we're being broken apart and we're going back and different elements are being broken apart, which I guess, which we could, if he wanted to describe light like that, saying that the more you break light down, the more, but you can break red down and into all of these spectrums and then break that down into all of these spectrums. And I mean, what do you mean it's more pure? I'm not really understanding that, because things are broken down continuously. It's an infinite, you know, infinite breaking things down. That's how the universe works. So when you say it's purest form, it's just funny to me. But let's keep moving. I'm just wondering, how do we know that if we put an apple in the air and launch it at this speed, it would actually, we would find it flipping back around? Like, that's the thing for me. How do I know it's gonna spin around. Now, I ain't never seen that happen before. I never heard of it. We never did no experiment. Ain't nothing like I ain't never like. That's what I'm saying. What he going through right here. Like, let's keep it moving though.
6,371
Then
kilometers
I'm
to
seeing that
meters.
667, and I'm like,
And the
man,
mass
this
of the
is
Earth is
670 this time.
about 6 trillion kilograms. Yeah, it's kind of a big deal. Okay, we insert our values into the equation. Big G, the mass of the Earth, over the sum of the two radii. And just a little bit of equation feng shui here. Get that out of the way. And before we grab our calculator for the plug and chug, let's do a dimensional analysis. The meters divide out one of those meters. Kilograms divide out one of those kilograms. And remember that a Newton is a kilogram meter per second squared. So when we substitute in a kilogram meter per second squared for the Newton, we get a kilogram meter squared per second squared in the numerator and kilograms in the denominator, which divides out, leaving us with meters squared per second squared. Take a square root, we get meters per second. Okay, now for some plug and chug. And we get 7,660 meters per second. Holy applesauce, that is one fast fruit. 7.66 kilometers, that's about 5 miles a second. That speed would take you from Detroit to Orlando in less than 5 minutes.
So my question also, will we have to equivalate for the speed, right? Because we got a lot of things going on. Like, okay, if we're not worried about the moon's gravity, we're not having to put into the equation Saturn's gravity pulling us or pulling the apple down. I mean, you're not really putting everything in the equation, right? Why you ain't putting the moon into it? You closer to the moon now. You're gonna have to be close to the moon in order to send. Right? Or you're just saying if we just lifted it up off the ground a couple miles or whatever, then or whatever, right? So we're not. What about the gravity of the moon? What about the spin? Right? Does it matter that the moon is getting closer to, like he's talking about the moon is getting closer? Does that matter? Does it matter that the sun is getting closer to the earth? Do we need to put anything, put these things into the equation? I know it might make it seem more complex, right? But we put all that in there. He didn't put in the mileage of the earth, he put the radius in, right? But what about the other objects? How do you know the radius if you've never been to the core? If you've never been to the core, how can you even put the radius in there? And you know how far the apple's going to travel. How do we know it's 24,000 meters or whatever that number is? 24,000 something miles, something like that, per square feet, something like that. How do we know that that's the number? Can we can we prove that? Has anybody ever done an experiment to prove that this is the radius of the Earth, or that we can't reach the sun, but we know that the sun is 93 million miles away? It's I'm just. How do we know these things and we ain't been there? They'll tell you, you know. Oh no, man, we ain't been there. A lot of them will tell you we can't leave Earth's orbit. So how was we get 93 million miles away? They say we can't go back to the moon. How do you know how far away the sun is for sure? I mean, how big it is. How you honestly know how big it is. What kind of technology you got to measure that kind of stuff, right? And they're telling us this is it. This is it. 24,000 miles. Hey, this is it, guys. This is it. The moon. This is where the moon know this, guys. We got the best scientists. We know these things. But do we know? I'm just curious. And a lot of us flat earthers, and we go back, we be like, damn. Do they know what the fuck they talking about? Do they know what they talking about?
Is that right? Does an object orbiting at 420 kilometers up move at 5 miles per second? Well, if you were to ask these 4 research scientists how fast they needed to be going to catch up to their orbiting lab, they would tell you that is precisely how fast it's moving. The International Space Station is a flying laboratory the size of a football field, 420 kilometers above Earth's surface. The ISS is moving so fast that astronauts aboard are treated to several sunrises each day. How many sunrises, you ask? I'd ask the astronauts, but they've been very busy lately and haven't been returning my calls. Let's figure it out for ourselves. First, let's draw a picture. Here's Earth, and here's our space station. By the way, isn't it cool the leaves of the apple and the solar panels of the space station basically do the same thing? Turn sunlight into usable energy? I think that's pretty cool. Anyway, we'll use the speed equation to tackle this problem. Speed equals distance over time. For t, we'll be using an Earth day, a 24-hour period. For d here, we want to incorporate the number of sunrises, which is the number of revolutions the ISS completes in a day. We'll call that n, which is the value we're looking for.
So I gotta hit up some Globers here because they're looking at this and they're probably like, "Hey man, what you got to say about this?" We can't prove it, man. I've never been in no space station, bro. To be like, "Hey, yeah, man, this is it, man. This is it, man. We way up here, man. And we going. I see all these sunrises, bro. No, man. What we can prove is that, well, now the one people who will talk to us for real is pilots. And pilots, a lot of pilots will tell you, yeah, man. You know, I done seen cats say, yeah, man, we follow the sun. We damn near followed the sun, right? I know one guy said he was in the military. He had 2 birthdays. He said that he followed the sun. Or he had another birthday somewhere else. You can follow the sun. So, and that's the flat joint. So we can go in planes. We can talk to pilots. We can talk to our cousins and aunties and all of them about the equipment, the tools that they use that balance things that I can't remember what it's called. But it's a tool they got to where when they balance and the it's like a cross, right? And they got to weigh it out with the ground, right? And that it only work on the flat surface. That's the only way it works. It don't work on no spinning globe, right? At what point we spinning it like the speed of a bullet or something like that, right? At what point do we get sucked in or do we start losing the atmosphere? At what point does we start being like, whoa, man, that thing going fast there, you know, because you got a point where an object is spinning in the middle and then the atmosphere around it is it's pulling the atmosphere, but you get to a point where you're gonna feel it when you're going so fast, coming off of something, and you're gonna feel that something's spinning. Where is that? There's no danger there. When they shoot these things, they shoot them straight up, right? But we see them curve. But they shoot them straight up. They're not worried about the speeds. What they're spinning like the speed of light. How is this thing staying in orbit, spinning at the speed of light? Spinning it, I mean, not like the speed of like a bullet and all of that. Like, it still don't make sense. It don't make sense. It still don't make sense to me. And they should be getting closer to the moon. Moon should be getting closer. all of that. You talk about the Van Halen belt, the belt that's all the way on the outside that they can't reach past because they got all of these asteroids and stuff, the asteroid belt, right? And they say that they can't get past the asteroid belt. That's kind of crazy. So to me, it kind of sounds like an electron. Back to the electron. And it's saying the valence belt on the outside, this is where you got the movement of the electron, where the force comes through. But beyond that, it don't push over. So you're saying that maybe beyond this atmosphere that they're speaking of, this is where things is pushed. Like, I don't know. I'm trying. I'm man. I gotta try. I gotta try for y'all. Cause I'm that dude. I'm the dude who will try. I'm the dude who be like, okay, man, well, let's see how they might be seeing this thing work. It don't work. It's so funny, man. I'm about to lose my head over this, man. Darn.
Now, assuming a circular orbit, the distance traveled for one revolution is the circumference of that orbit. So, the distance traveled in one day is just the number of revolutions made in a 24-hour period times the circumference of the orbit. And circumference, of course, is just 2 pi r. Okay, we've broken this down as far as we need to because we have all the values.
And that's what I'm saying. How can we prove the distance traveled in one day? How can we prove how many days it take to travel the whole joint? How can we prove they really doing it? We just being told this, man. You look up and they see you seeing one of the skies, and man, we live in a day now where anything can be fake, man. The deep fakes is real, boy. Y'all got to check out the deep fakes. They are no joke, man. We talking about top-notch scientists and engineers, electrical engineers with computers and stuff, just throwing us images, man. And we going along with it. You know what I'm saying? We ain't here understanding the double talk behind what they saying. These guys, they talk like, damn. Let's keep this moving, man, because I got to go get my card. I'm gonna see if we can just finish this video, though. Let's finish up.
Values except for n, the one we're looking for. So we need to solve for n by multiplying both sides by t over 2 pi r, which gives us n equals vt over 2 pi r. And this r is the sum of the Earth radius and the altitude of the space station. We'll rewrite this. Last thing we need to do is convert one day to seconds.
You can't prove that's the Earth radius. Let's go.
Equations say yes to the MKS. So after a quick conversion, we get 86,400 seconds in a day. We'll do a quick dimensional analysis before we grab our calculator. And the meters divide out, and so do the seconds, which is good because we're looking for just a number. Now we can plug and chug, inserting our values. And we get 15.8 sunrises. Does this value answer our question? How many sunrises do they see? Wait a minute. Can we have 15.8 sunrises in a single day? No, that makes no physical sense. You can't have partial sunrises. So the astronauts aboard the ISS see 15 sunrises on some days and 16 on others. Can that space station stay up there forever? As long as we're willing to keep going up there and giving it a little boost. You see, it turns out that even though the atmosphere is very tenuous at 420 kilometers up, the collisions that do occur with the particles that mill about at that altitude cause a very tiny amount of drag. And remember, tiny things can add up over time. So over time, it reduces the velocity of the space station. Going back to Newton's thought experiment, reduced velocity causes a decrease in altitude, bringing it in contact with denser atmosphere, which increases drag, which reduces velocity, which, well, you get the picture. It's a gradual death spiral for the space station, culminating in a fiery re-entry into the Earth's atmosphere like this one. This is a picture of our 1970s space station Skylab re-entering Earth's atmosphere and some of the remains that were found in Australia. To keep our ISS from going the way of Skylab, visiting rocket ships fire their rockets while attached to the space station to help it regain lost altitude. Suppose we were to keep firing the rockets, drifting further and further from Earth. Eventually, we'd reach the orbit of the Moon, which is exactly what we did in 1969 with Apollo 11, humanity's first lunar landing, and we coordinated the rendezvous with just the celestial mechanics that Newton gifted us. And we are going back in a few years with a space station that's being...
Somebody said it too, right? When the flat earth, this and that's real. How come in that picture we never see the picture of the earth in the background? The earth should be huge. Earth should be huge right there. It should damn near take up like a lot of that right there. All of that blackness is right there. How come you never see it? All in the picture that they do show you of the earth. The earth is in the background. It looks like it's the size of the moon. See, so from the earth, how do you have a picture where? I'm sorry, man. Let's look at that. I think that's good. I think that's a good hit. Let's take this gravity search. It's going to be around too much longer. What we're gonna say? Let's see. Earth. Moon image. Here we go. Okay. Now look at that. Look at that. These images. Okay. See, now this is more like it should have been closer. This is not even a real picture. Look how close this is. This is more like how it should have been. More like it. It should have been bigger than that. Should have been able to look over and see that. Not this. Not that. Okay. We needed to see something a lot closer. And notice they got all of these different images. Right? But yeah, it should have seen. We should have seen something like this. How come we've never seen the earth like that from the moon? How come it was way in the back like this here? Or like, they gave you this view here. First view, they say. Look at this thing. It should have been closer. Look at that. We ain't even breaking it down right now. But we just looking at them, just throwing y'all this something else. Because I know a lot of people might be just looking up flat earth stuff. But this is how we should have seen it. It should have looked like this. Something like this, a little closer. It should have been, but we're not giving that image. That's not the image we're giving. That is not the image we are giving. Okay? And we see all of these images is fake. We look up Earth from the moon, we can't even get a real image. Like, look at that. The moon fake is on the way here. Right? Look at that. I gotta do a test real quick. Test. 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 Okay, because I can't hear myself no more. Alright, that's all on my sound card. My sound card just died on me. You get yourself a sound card, man. Charge that thing up, man. Okay. So, um, alright, yeah, y'all got that. Let's keep moving. My stuff dying on me now. My equipment dying on me. I got to lay it down for work anyway soon here. Let's keep moving.
We are going back in a few years with a space station that's being built just for lunar orbit. Gateway, the forthcoming lunar space station, will be an orbiting outpost for long-duration visits to the moon, and a stepping stone for our next giant leap, which will be sending humans to walk on Mars. How fast will the Gateway space station need to be going to match the orbital velocity of our moon? Well, we're dealing with the same physics here, so we can just borrow the modified equation from our Apple problem using a few different values for the plug and chug. For R now, we need to use the sum of the Earth radius, the moon radius, and the Earth-moon distance. Looking up
Should be good. Yeah. So I just want to say, man, you got to be moving fast in order to catch objects that's moving that fast. As they claim that the moon is moving and we're spinning like a speeding bullet. We're not really paying attention to the speeds in which we're spinning, and that's what I'm saying. Like, you and I will never be able to build a rocket to go to the moon because we have to incorporate all of the stuff that NASA did. You have to have millions of dollars worth of satellites and equipment and all that to make your own transfers. Otherwise, you're gonna be going through like their checkpoints and stuff. So, say this stuff is real. They're building a thing to where you have to go through them. You can't do this on your own. You have to have NASA or the government or whatever to help and back you up, whatever government. So this is a form of control. It's like limiting. It's like saying, well, man, the only way you can get to outer space is if you use this technology that we built right here. You can't do it. You can shoot off rockets straight into the atmosphere, right? Straight up, right? And they got videos of people doing it. But then they don't have to account for no spin, no bullet speed spin, or no crazy, nothing like that. They go straight in the air. You know what I'm saying? There is no difference. There's no point where the speed catches you. It's imaginary. It's like, man, when we're spinning, you can't even prove you're spinning. So how do they know that that we're spinning at bullet speed? If you can't send an object up there to prove to me, if you send something straight up in the air, that it's gonna come out miles and miles away, or it's gonna spin. The Earth is gonna spin all the way back around, and it's gonna fall back down. Or if you shoot a rocket, like the dude was saying, a cannon or something, it's gonna go all the way around and come back. If you spin it at a certain velocity, you can't prove any of this stuff. It's all theoretical.
up values for the moon radius and the Earth-moon distance and converting to meters, our equations say yes to the MKS. And inserting our values into the equation, big G, the mass of the Earth, and the sum of the two radii and the Earth-moon distance. A little dimensional analysis, just to make sure we'll get meters per second. And it looks like we will. Good. And then we plug in chug, which gives us an orbital speed for the moon of 1,010 meters per second. So, is that how fast Gateway will need to be traveling when it gets to the moon? Not so fast, or perhaps not so slow. Remember that the orbital speed of the space station is set by the mass and radius of the body being orbited, as well as the orbital altitude. So, once again, we need to solve our modified equation here with different values. The m in the equation now represents the mass of the moon, because the lunar space station will be orbiting the moon. Here's that value, by the way. And the r represents the radius of the moon, plus the radius of the space station, which we'll ignore for obvious reasons, plus the altitude. There's no atmosphere on the moon, which means no atmospheric drag, so orbital decay and fiery death spirals aren't much of an issue. So long as we're higher than the highest mountains on the moon, which are about 5 kilometers, we'll be fine. 100 kilometers would give us plenty of clearance, but let's use a
Astronauts, you can actually look at the videos, right? And these guys are jumping and they fall, and there's an obvious drag there, right? They're not like all light and stuff, like floating in the air and stuff. No, they're just jumping up a little bit and then they're coming down. They exaggerate that here when they give it to us in the media and like it's propaganda, and they built these toys and stuff here that we play with, and they put it in the movies and stuff. It's always this, oh, you're lighter than you're really really light. No, when you see these astronauts, they're not really all that light and stuff like that. There's an obvious drag. So let's just keep that a band, okay? So yeah.
111 kilometers in honor of the world's best wingman, Michael